Okay, thank you. So maybe we can change it. Yeah. No, 它全这个。哦，这个是它控制的选择。Okay, that's okay. So first, thank Chao-Gan who invited me to have this talk. In fact, he also invited me last year, but unfortunately, cannot go to my visa to Canada. But I'm very glad to have you all to share some idea about our study, especially on the Brainnetome atlas. So I think this is a very important tool to study different, for example, to find the biomarker for diagnosis, also for the neuromodulation, especially. So today I just focus on how to use the Brainnetome atlas for the neuromodulation. So I don't know how to explain. 啊？按这个吗？它这个，要把这个放下。可以放，往这边放。So firstly, I'll talk about what is Brainnetome atlas. So then I'll give a detailed discussion how to use Brainnetome atlas for the localization and also how to find some target stimulation and so on. So in fact, for the Brainnetome atlas have a very long history. I think at least over 100 years. So the first one is Brainnetome atlas. So this is atlas just developed by use the Sato architecture. So just means the shape, cell shape. If the shape is similar, should belong to one brain region. If different, should belong to different brain region. So then we can find the boundary between different brain regions. So, but here, I try to a very different way. This is why we call the Brainnetome atlas, not just the Brain atlas. So, in fact, for the Brainnetome atlas, the methodology is very different from traditional. So we use the anatomical connectivity as the method. So we just compare the two works. So if two works' connectivity profile is the same or similar and some threshold, we think these two works belongs to one brain region. If they have a very different connectivity profile, they should belong to different brain regions. So based on this kind of idea, we can pass that some brain regions into very fine-grained brain regions, such as this one. This is called the medial cortex. So for this brain regions, post-medial cortex, for this brain regions, in fact, you based the Sato architecture, you can also pass that into different parts. For example, for this brain regions, use the anatomical connectivity, we can pass that the post-medial cortex into 5 different parts. So in fact, each different parts with different connectivity profile. So on different data set, we can get this very similar result. So this is show for 5 different brain regions, we can get the 5 different connectivity profile. So in fact, for the some brain regions, the Sato architecture is very maybe heterogeneous, but for some brain regions, such as the temporal core or front pole, for this kind of brain regions, the Sato architecture is very similar. I mean, this kind of brain region is homogeneous Sato architecture. For this kind of brain regions, it's very difficult, or if maybe it is impossible to pass that into different parts. So in fact, for this kind of brain regions, I think over 100, or think it's just one brain regions. But here we can also pass that into 3 different parts, also with different connectivity profile. So this is a connectivity atlas. So in fact, after about 6 years, we finished the full brain pasteurization. So we passed the cortex into 210 different parts. But for subcortex, 36 different parts. So totally 246 different parts. This is the Brainnetome. Besides the presentation, we also provide you with the anatomical connectivity profile. In fact, use this kind of profile, you can do a lot of things. For example, you can predict, so for each part, what is function involved. So now, I'll try to show you how to use this kind of Brainnetome for the neuromodulation. So the first things I'll talk about how to find the accurate localization of stimulation target areas use the Brainnetome. So then we also talk about how to find some optical coil poster, for example, especially for TMS. So besides, you should find some target stimulation regions. You also need to decide which post should put for each regions. So this is a very difficult topic. So in fact, we also try to show you some current studies. So use the digital twin brain to predict the stimulating target areas. So what is best one? So first I'll talk about, in fact, here I just show you an example. For example, for the TMS, we always just stimulate the dorsolateral prefrontal cortex for different diseases. For example, depression, schizophrenia, even Alzheimer's disease, always stimulate the same regions. But this is a little bit ridiculous. For example, so from Brainnetome, the dorsolateral prefrontal cortex always divided into at least 4 to 6 different parts. But the different sub-regions always have different function. So here I just try to show you, use the Brainnetome, you maybe can find the accurate localization. So this is for the non-innovative stimulation. But also for deeper brain stimulation, we also need to decide which parts we should stimulate. For example, for Parkinson's disease, we always stimulate the, let me see, so the STN. So this is a benchmark for deeper stimulation. But as you know, in fact, for the Parkinson's disease, always there are some, bystander effect. So for example, 30% maybe has no response or with side effects, something like this. 20% maybe will be changes the cognitive function and so on. So why? So no one can tell you. But if you from the Brainnetome, you can tell you. In fact, because the STN can be parceled into 3 different parts. One is related to mood, one is related to emotion, one is related to the cognitive function. So if you put the record just on the motor areas, so this is fine. So if we put some other areas, so maybe some by effects will happen. So these 2 examples just show you. So if we use the Brainnetome, maybe you can improve the stimulation effects. 怎么这个不动了？这个怎么动不了了？这个是有视频吗？它可能有个视频，那个好像不是视频嘛。那翻页能翻得动吗？这个翻不动了，你看，这个从哪个呢？
这现在是他在控制。现在是他在控制吗？
这个搞不清楚啊，我这个 这个原来4个就是还可以。
OK，从头开始拉。
So could you move to does it work?
Stop. Cannot move ahead. 是按也没有用。
没用。
现在呢？
No.
Sorry for the technical issue.
So could you go to this one?
Next and previous. And this one, previous.
Hmm?
It's okay.
Okay, thank you. So in fact, so in these two slides I just told you, use the Brainnetome atlas, you can find maybe where is exactly we should put the stimulator. So in fact, if we can tell you, so which part you should put, but for different people also have different effects. For example, some people maybe can just put the motor area, but some people also put into some other parts. So in order to address this kind of issues, we developed robots. We call the Brainnetome atlas guided neuromodulation robots. So use this kind of things, we can address the TMS, TDCS, and DBS. All these kind of things can be used. This kind of robots to address that kind of issues. For example, this is a kind of application. Anyway, in fact, another big issue is individual difference. For example, for different people, always the shape is very different. So we also develop Brainnetome atlas individualization. So because the time limited, I just scan this one. If you're interested, we published on the translation, attribute transaction on neural network and the learning system. So this is very easy to got it. So another topic is about how to put the coil. So in fact, the first part I just told you where we should put, but what is the poster? So this is another big issue. So in fact, here we try to establish the effect relationship because the coil always put outside the skull, scarf, but the effects on the cerebral cortex. So we needed to establish we call the stimulation effects mapping between the coil and the cortex. So here I just show you this one. So we call this kind of atlas is the here, the optimal placement atlas. So this is, in fact, we have 246 different parts, and for each part, we can tell you, so what is the angle, so you should put your coil. So this is the second part, and also a very difficult question we needed to address. So the third one, when told you, put here, put here, put here, so which one is best? So, but address this kind of issues, we proposed we use the digital twin brain. So digital twin brain includes 3 parts, three components. First one is the twins, the basis. So we said that maybe the Brainnetome atlas is the bridge between digital and the biology of the brain. So here we take one examples. So to show you how to use the digital twin brain to address the best stimulated target areas. So in fact, here we take the methamphetamine abstinence. I'm not sure how many people know this kind of things. So this is a very popular drug. So here, this is the outline for this kind of study. First, we need the real data. So means some people take the methamphetamine. So this is only some very special population. So we scan the functional MRI and also the diffusion MRI and the structure. Only these three is enough. So use this kind of things, we can construct a digital twin brain. So then we to evaluate so how for different time abstinences. So what happened and so on. So the first thing is we need to construct a digital twin brain. So use the Brainnetome atlas. Then we can go to the connectivity, topic connectivity. Then we can also use the functional MRI to find the functional connectivity with these kind of things. So then we needed also on the digital twin brain, I mean so on the each brain regions, we modeling the functional signals. So use this kind of signals, we can evaluate. So in fact, we can change each part of brain regions from a signal, but this is digital. So we use a very simple model. We call it Hopper model. This model, in fact, is from the physics. So here, only one parameter, alpha. So this is alpha greater than 0 or equal 0 or less 0. So only 3 states. But use this kind of data, we can find very interesting things. For example, here we first change each part of brain on the digital twin brain. So then we can evaluate the behaviors. So for example, we can find so change these brain regions, how it improves the abstinence. So change another one, so we can compare. Then we can go to the best one. So use this. So here, very interesting, we find the best one is nuclear carbon. So in fact, especially for the methamphetamine abstinence, so the neurocarbon is the best one. So if some clinical just try to maybe select this parts, and so this is very consistent with the clinical practice. So more important, if we cannot stimulate the neurocarbon, maybe which another one, for example, on the cortex, if we just want to use that TMS to stimulate it, so which one is best? So we found the sample regions is connected with the neurocarbon and also belongs to the reward system, so is best. So here, I just also do some other correlation between the improvement with these kind of things. So anyway, here I'll show you one example, how to use digital twin brain to find the best stimulated target regions. So you can also use this kind of model to study, for example, TMS or TDCS or any other things. For example, if you got a data for depression or schizophrenia, you can also use the same protocol to study this kind of issues. So anyway, here I give a very brief summary. So we show you Brainnetome atlas. I think this is very useful for diagnosis, for stimulation, and maybe also for digital twin brain and so on. So in fact, in my teams, besides that studies the Brainnetome atlas, for example, we study how development affects the Brainnetome atlas, how aging affects the Brainnetome atlas, how different diseases affect the Brainnetome atlas. So another very important direction is based on the Brainnetome atlas to develop some image biomarker with this kind of things. In fact, we also have a publication on Nature Medicine. Just use Brainnetome atlas and big data, then we can find some image biomarker for diagnosis. So in fact, another very important direction is based on this kind of, with Brainnetome Atlas, we can also develop some brain-inspired computing models. So in fact, maybe next time I can show you some data on this direction. Okay, I'll finish here. Thank you.
Many thanks to Professor Jiang's wonderful talk. We will limit the questions to the panel discussion. So let's move to the next speaker. The next speaker originally is Dr. Robin Cash, but unfortunately he got a health issue. But Andrew Zhao, he will present on his behalf. And Dr. Andrew Zhao is from University of Melbourne. And lots of people, I think you are using history books like NBIs or using the subcortical atlas. And lots of work. Please join me in welcoming Professor Zhao.
Thank you very much for the kind introduction, Professor Chao-Gan. I appreciate it. As Professor Chao-Gan noted, I'm presenting on the behalf of Robin Cash. I'm Robin's supervisor, and unfortunately, Robin's fallen ill. So I'll try to do his work justice, but I only received the slides a couple of hours ago. So if what I say is slightly disconnected from the slides, please forgive me. So here I'm going to present an alternative approach to what Professor Jiang has already presented to personalize brain stimulation coordinates. This is a method that we've developed in Melbourne. We developed this with Dr. Cash a couple of years ago now. And since then, we've implemented this approach clinically. We're using the approach to personalize TMS for patients with depression. And we've already treated approximately 90 patients with this personalized approach. And looking forward into the future, we're going to use this method to, in a clinical trial. Just as an overview, if you would like some further information, we recently published a review. Robin and I published a review in Biological Psychiatry. I've given you the first page there. And this has got a lot of the details and issues and limitations of fMRI-based personalization for TMS. So check out the review if you're interested in further details. So brain stimulation in psychiatric disorders. We've specifically focused on treatment-resistant depression, and typically TMS is delivered to the dorsolateral prefrontal cortex in depression. And we know that is a site, that's a region that gives a high efficacy. The problem is that clinical outcomes differ substantially across patients. Some patients respond really well to TMS treatment, others don't respond at all. And we don't have a good understanding of why there is considerable variation across patients in treatment response. But we think that there are various factors. These might be demographics, there might be differences in clinical profiles. And in this work, we've specifically considered whether there are differences in a patient's functional connectivity architecture and whether these differences are what contributes to why some patients have a very good response to TMS and why others might not do so well. And so the whole idea of personalization is to choose a site that specifically matches a patient's functional connectivity architecture. Here's an example, an analogy. We know that for the motor strip, there are very specific areas that are responsible for particular motor functions. And so the analogy here is that for the DLPFC, we also need to, rather than looking at the DLPFC as a whole, we need to focus on specific areas of the DLPFC. Now, typically, TMS for depression is delivered at a group average coordinate. So all patients, when they come into the clinic, the TMS coil will be placed on more or less the same position, the same site on the scalp. But we know there is considerable variation across individual patients in not only the structure, the cortical folding, the sulci and gyri, but also connectivity. And so over the years, we've seen that targeting approaches have evolved from a simple 5 centimetre rule. Some of you in the field may be familiar with this, to using the F3 coordinate of an EEG cap, anatomical targeting, and now, as I've shown there on the far right, the current state of the art is using fMRI and fMRI connectivity to personalise an individual patient stimulation site. So what do we mean by structural connectivity? I'm sure most of you here are probably very familiar, being human brain mappers are very familiar with brain connectivity. There are 2 types of connectivity. Structural connectivity, we infer that from diffusion MRI and tractography. This is mapping the physical fibres between different brain regions. And we also have functional connectivity. This is what we would derive from resting state fMRI, and this represents the statistical dependencies or the coupling between distinct brain regions. And in our work so far, we've only considered functional connectivity, but of course there is scope to extend this and to potentially personalise, not only based on functional connectivity, but also structural connectivity. Now the question is, what kind of, or where should we be measuring connectivity to, right? We're interested in stimulating the DLPFC, which is a large region, and we want to use FC to personalise connectivity, but where would we measure that connectivity to? And we've generally focused on a region called the subgenual cingulate cortex, and the reason for that, the rationale for that, is that there is extensive work that has shown that MDD treatment response the SGC is an indicator of how an individual, how a patient will respond to TMS treatment. So the basic rationale is that TMS cannot directly stimulate the SGC. So the SGC is deep within the cortex, and TMS can only penetrate the surface. But if we stimulate the DLPFC, the idea is that there is a putative connection. It might not be a direct structural link, but perhaps a polysynaptic link, and that stimulation will travel from the DLPFC along a white matter fibre or multiple white matter fibres to the SGC and achieve the desired effect. Now the question is this feasible? So can we use a person's fMRI scan to reliably compute a stimulation target on the DLPFC based on its connectivity to the SGC? So we know that there are many limitations of fMRI, right? There are issues of reliability. If the person moves their head in the scanner, this can induce noise. There are these whole issues such as global signal regression and so on. And some of the early work in this field by Ning and colleagues suggested that we can only localize a coordinate in the DLPFC to an accuracy of around 3.5 to 4 centimetres. And this is probably not enough precision to enable personalisation, even with very high quality scans. So our first goal, what we worked on in 2021, was to develop a new algorithm, a new approach to personalise coordinates on the DLPFC with high precision. We aim to achieve a precision to within a few millimetres. And we were able to do that. I'm not going to go into the details of the algorithm. You can check out the HBM, the Human Brain Mapping paper there on the bottom of the slide for the algorithmic details. But really, in a nutshell, we use a clustering approach where we compute connectivity from the SGC to all coordinates within the DLPFC, and then we cluster areas of negative connectivity and then use essentially the center of the centroid of the cluster. And using that approach, we can achieve high precision. We can localize to a precision of a few millimeters, 2 millimeters, as Robin's put onto this slide. We see that we preserve inter-individual variation. So a very important point here is that when we personalize, we don't want to just make sure, we don't want to have it such that each coordinate that we compute for a patient is the same, right? So we don't just want to output a group average coordinate. We still want to preserve variation across individuals. And we've ensured that our approach achieves preservation of inter-individual variation. And we've also shown that personalized stimulation targets are heritable, and that gives us some hope that what we have here is the variation that we're capturing here is biologically meaningful from a genetic perspective. So this is just some further info on the reproducibility, the specificity of our approach. I won't spend too much time on that, and we've shown that we can achieve a good spatial correlation as long as the acquisition time of our fMRI is around 15 to 20 minutes or more. If we have a very short scan, say 10 minutes or less, that doesn't give us enough data to enable a precise or a reproducible coordinate to be computed. So, okay, that's all great. We've developed an approach to personalize. We've shown that it's reliable. We've shown that we can achieve good precision to within a couple of millimeters. But the real question is, does this have clinical relevance? If we take a patient's fMRI scan and give the clinician a personalized coordinate, is this actually going to improve the clinical outcome of TMS for a patient with depression? The first thing that we did to test this is we had data, retrospective data, where patients were treated using a one-site-fits-all approach, so a non-personalized approach. Basically, they came into the clinic and they received standard TMS stimulation. Now, there is inherent variation across patients in that process, but once again, I'll emphasize it was non-personalized TMS. And then we took an fMRI scan in those same patients as well. So what we did, we knew the person's actual stimulation coordinate that they received stimulation at, and we also had their fMRI scan. And so what we did, we applied our personalization algorithm to their fMRI scan and computed the optimal coordinate for that patient. So we had the actual coordinate and the optimal coordinate. And what we did, we computed the distance on the cortical surface between those two coordinates. And we hypothesized that for patients where that distance was very small, so where just as a matter of chance, the optimal coordinate was actually the coordinate at which the patient received TMS, they were both very close, that we would see a better treatment response for those patients. In contrast, if the patient was unlucky and the distance between their actual coordinate and their optimal coordinate was quite large, we hypothesized that treatment response would be poorer. And that was, in fact, what we found. If you take a look at the scatter plot on the bottom there, the y-axis, the vertical axis there, is showing improvement in depression severity. That's measured using MADRS. That's a clinical depression scale. And the x-axis, the horizontal axis there on the bottom of the slide there, shows the distance between the optimal coordinate and the coordinate at which the patient was actually treated at. So this verified our hypothesis and gave us some hope that personalizing would be useful. Once again, it's important to emphasize that this is retrospective data, right? So this was analyzed after treatment, and there was no personalization of treatment here. Now, we also compared this to a group average side, and we showed that a group average, we never had this relationship. I won't go into details of that there. So this suggests that targeting is feasible. Interestingly, we published this work in JAMA in 2020, and since that time there are many groups that have replicated this finding in independent cohorts. So I've shown a couple of work there. Once again, this is the same approach. The y-axis in all of this work is treatment response, and the x-axis is the distance between the actual and the optimal coordinate. And we see that there is a significant relationship between the two. Yeah, so there's some other work I won't focus on. I'm not quite sure what Robin had in mind there, but I'll skip over that. So what we're at now we're at the stage of actually clinically translating this. And last year, or actually, yeah, just over a year ago, we set up a clinic in Australia where we're now implementing this personalisation approach. A patient comes in, we take their fMRI scan, we apply our algorithm to their data, compute the optimal coordinate, and then we deliver TMS for a period of 3 to 4 weeks to patients. And we've had approximately 90 or so patients with depression come through the program. We're also running, or we're just in the process of setting up a clinical trial in Australia for this approach, and this will be run across Melbourne, Sydney and Brisbane. We've also done some work where we've shown that personalisation can improve TMS for memory performance. These are from some collaborators in Melbourne. I won't go into the details of that. This has also been used for some work in substance abuse, and I think our next speaker will touch on this. This is some collaboration, so I won't spend too much time on this, but this is the same approach. This approach has also been done in some collaboration in an autism data set with Professor Suyan Duan, and also in post-stroke aphasia. So we can see that there is a burgeoning of studies here that are focusing on using fMRI, either fMRI connectivity or structural connectivity, to personalize coordinates for neurostimulation. So I'm going to wrap up there. And once again, I'd just like to acknowledge all of Dr. Cash's work in this area, as well as our other collaborators that are listed there on the slide. Robin's listed some key papers there in the central column, so if you're interested in further details, check out those papers. And if you're just wanting an overview, I'd recommend checking out that review paper that's listed on the right-hand side of the slide. So thank you very much, and I look forward to the discussion at the end of this session. Thank you.
Thank you very much for the wonderful talk, Andrew. I believe there's lots of questions, but let's remain them at the panel discussion. So next speaker is Dr. Eduardo Garza-Villarreal from National University of Mexico. And probably you will answer Andrew's question, right?
A little bit.
For the application. Okay, welcome.
Thank you. Okay, thank you for inviting me. And so I'm going to talk about what we're doing in addiction, and we're collaborating with Robin. And so that's something I'm going to talk about. So I have no disclosures. So substance use disorders, as you know, are a worldwide problem. Different drugs in different countries, however, it is a problem. And it's considered a neuropsychiatric disease. And well, basically, people have inability to control the use of the substances. And it could be legal or illegal, so it's a huge problem, especially with alcohol. Right now, there's a huge issue in most countries where you can actually drink alcohol. And it could go from, very little to moderate to severe in general. And the problem is, of course, limited treatment. So that's why we're using other techniques like TMS to try to treat patients, because none of it is working at the moment. And well, I'm going to present some work about cocaine, which is a stimulant drug, and a little bit about some alcohol. And well, in general, I think Andrew talked more about this, which is basically the idea that if you use functional connectivity and try to see who gets better where they are stimulated, then you will see that depends on where they are stimulated, they will have a better or a worse outcome. And this comes from work from Robin, but also from Michael Fox. And basically, the idea is that you need to stimulate areas in the brain that are more deeper than you're actually stimulating with the TMS, with the idea that we have circuits and you're affecting all the network when you're stimulating them. So, and at least that's the main idea. Of course, it is a hypothesis. We don't really know if this is true yet. So, yeah. And then this is some work that you can see from Hamed Ektiari, who basically published a meta-analysis saying, well, where is everyone actually stimulating? And for different drugs, but in general, using TMS, for example, here you can see the left dorsolateral prefrontal cortex and the right one are actually the places where most people stimulate with TMS. But there are also other targets that maybe we can find. But basically, this is the main area that most people are stimulating. And so we're focusing on that area because traditionally from from depression, but however, it also has potentially, it's relevant to the connections it has deeper inside the brain. And this is just in general that it also depends on, in the case of substance use disorders, when are we stimulating? Is it for recovery? Is it for detoxification? Pre-treatment, post-treatment? I mean, depends on where you stimulate, of course. We don't know exactly if it's going to work for all of these stages. And depends on this is different studies in alcohol, cocaine, etc., where they actually studying it. So there is a lot of work to be done here. However, we know that in most published studies, and this is with nicotine craving, for example, most studies with TMS show that TMS works to reduce craving, and that is the need for the drug, but also the drug use, which is our standard. And also with methamphetamine, cocaine, we're seeing this in different studies. However, targeting methods are just basic targeting methods. In TMS, we use either the 10-20 system, clinical settings use that, or now there's another one called the BMF3, and there are other ones, but the most used are those. So very few places are actually targeting with, for example, MRI and using neuronavigation. So again, with alcohol, we're also using we see some papers that show that there's reduction in craving. Other ones, we don't see that, so that's interesting. And yeah, why is this possible? We don't know exactly. However, there is a hypothesis shown by Marco Diana here, where basically when they did studies in animals, they see this effect when they stimulate the prelimbic cortex in the rats and the mice, sorry, and then also in the rats, and because there is a connection with the reward system. And we believe that with TMS stimulation, where you're stimulating the dorsolateral prefrontal cortex, you're actually stimulating the whole circuit there. Or that's the idea. And with that, we want to reduce craving and increase abstinence days. So, and some studies, like in alcohol, like this study by Harel, for example, they showed that basically, if you stimulate certain areas like the dorsolateral prefrontal cortex, you can actually see that there is they found a decreased connectivity with the medial prefrontal cortex, and like for example in this case, medial prefrontal cortex with the ACC, for example. So they found a decrease there. So it's kind of like trying to also finding biomarkers related to TMS improvement. However, we still don't know exactly how is this working. And so in 2021, we published this study on cocaine addiction, but also I wanted it to be a data set that people could use, not only my study, but also like a study for a lot of people. So we did a preclinical double-blind randomized control trial. Not preclinical, sorry, clinical. So we had two main primary outcomes, which were craving and the cocaine consumption. And secondary ones, we have a lot of them, including impulsivity, which is seen in cocaine use. And we also have a lot of different variables that we wanted to acquire. And this is for also use for everyone. We acquired T1 weighted images, resting state fMRI, and diffusion multi-shell with a Philips Achieva, sorry, it's an Ingenia that we had for the clinic. And what we did here, we didn't have a neuronavigator, and this is something I want to share because people can do this, and everyone else can actually use it for this type of studies because, well, we didn't know exactly where to stimulate, like everyone. So instead of using a neuronavigation because we didn't have it, we just basically used the 10-20 system. However, we decided to use a way to localize the place in the brain and in the cranium, and then from there to the brain, using the MRI and a pill, vitamin E pill, that we used to localize it. And so what we did was gather data for where we're stimulating while using the 10-20 system and the BMF3. And from there, you can see that in the A figure, you can see where we're basically stimulating in different subjects. And in B, we can see like the seed of these mean stimulation. And for this seed, we used well, this is a map of the eNorm. Where basically what we did was first double-blind control study, the first 2 weeks of simulation, and then we had an open label maintenance. So it's 2 weeks of double-blind that we had. And we used the Human Connectome project, and using this seed that I showed before here, which is the mean area where we simulated, we basically, in collaboration with Michael Fox, we had the connectome of this region using the connectome project, and we constrain our search of functional connectivity differences or improvement using this map. And then what we saw was, at least in craving, and in craving we saw an increase. You can see in blue, you can see the active group, and we saw a decrease that was significant compared to the controls. We have a sham group. We also found improvement in impulsivity, which was good. But we didn't find any interactions between anxiety, depression, and sleep, which we were trying to find. So mainly just doing TMS, even if it was a sham TMS, worked for depression. So people were actually, but people were also in other treatments, so that also helped. So it wasn't specific for TMS. And then what we found was that there was the connectivity between the left dorsolateral prefrontal cortex and the ventromedial prefrontal cortex was the one that showed a high effect. In this case, we found an increasing connectivity between just 2 regions after the TMS, specifically for the real group. But we also found the connectivity in the ventromedial prefrontal cortex and the left angular gyrus as well, with some changes. So in general, we found changes in these regions related to the TMS and the improvement. And then when we look at the diffusion data, we use NAUTI because we had multi-shelled results, and we found that basically after simulation we found an increase in density of axons and dendrites. So in this particular tract, which is between the dorsolateral prefrontal cortex and the ventromedial prefrontal cortex, but also we found it in some subcortical regions. And we also found that specifically the subcortical regions, the first scan showed us that we could predict which subjects were actually going to get better with it. So that means that it may be, we can actually predict that depending on their structural connectivity beforehand. And it seems to be that maybe it was affected, and then when we improve it, then you can see this effect better. And it was mostly related to subcortical regions. And also, as I said, we wanted to open this for everyone. So after we publish it, I think open science is important for this, because when we don't know exactly if it's an effect of one study or another one. So the idea is to make this open. So we make this available for everyone. And this was just published this year, but it's basically a summary of how you can use the data, what does it have, etc. So you can actually use it. And we also, if you want the data, you can actually have it now. It's in OpenNeuro, and it's in Zenodo we have the clinical data, and in OpenNeuro we have the imaging data, and we have all of it. It's raw, and you can use it. It's in bits format, so it's ready to be used. And you can also contact us if you want to use it. I know Robin is using it for their own studies as well. And this has helped also, I think, because all other researchers have been using our data. This is just an example of other papers that have been published with our data. And I think it's, people are trying to use it for different things, not only the TMS, but as I talked to Thomas Yeo, and I didn't realize it was the only data set with open data set with TMS out there, but hopefully this will help more people to actually release their data, and I think it's a good thing. And for now, what we are doing now in our case is working with Robin Cash at the moment. We're basically running a study with alcohol use disorder, my student here, Alejandra, in collaboration with Anna Silverstan, Robin Cash, and Malar Chakrabarti. We're basically running a study where we're looking into using TMS, resting state fMRI to basically find the individualized area, as Andrew just showed you. And so trying to find that, then we try to simulate that area using neuronavigation. And we're actually we're using patients with alcohol use disorder, but they are already remittent, with the idea that we want to study if their improvement in cognitive flexibility will actually keep them in abstinence for a long time. And so we're trying to find, and I think I'm not seeing my other slide here, but I hope it is here, and I'll show you what we're trying to do. But basically, we'll have 4 weeks of simulation for these subjects. And we're also, besides fMRI, we're also getting data for resting state EEG, because also I think EEG is important to try to understand the whole picture. So we'll have this as well. And this is all going to be, of course, open when we publish. But the idea is to have patients with former alcohol use disorder and active and sham treatment, and then we'll also have controls for the fMRI that are not going to be simulated. And the idea is to simulate them for 4 weeks using, of course, the individualized target, and study them for a while, and then afterwards 6 months we're going to follow up, see if they're still well. And using Robin Cash's idea, we're using their individualized target, but instead of using the subgenual cortex that they were using for depression, I'm actually using the one we got from the cocaine study. So we changed the target, the subcortical target at least. And that changes, of course, the cortical target. So we're using it for each person that we're stimulating. And finally, well, we'll have some small results from but basically we're using, another thing we're doing is multi-band acquisition of fMRI. We have a TR of 1. We're trying to get better data for this and trying to also see what people can do with it. So this is just the results of 13 subjects with the task switch, with the cognitive flexibility task. But basically to show you that we have better representation of the Bose signal, because it's very small, because we actually get a better resolution, temporal resolution, structural resolution. And that's all I have with this study. We're starting, so I'll tell you more about it maybe next year, hopefully. And I just want to say thank you to my colleagues and supporters and my lab and my students. Thank you.
Thank you very much, Eduardo. And you are pioneering open science for the TMS dataset. Okay, the next speaker is Dr. Jing. Jing has worked at Stanford University and Harvard University and now at University of Iowa. And she will present wonderful results. Jing, please.
Thanks for the kind introduction and invitation. So I'm very excited to have this opportunity to present our recent unpublished work about the subcortical target engagement by invasive and non-invasive cortical stimulation and its relation with the individual functional connectivity. The 2 subregions we are interested in are currently focusing on the amygdala and the hippocampus. The 2 subcortical regions are implicated in the pathophysiology of a range of disorders, such as depression, anxiety, ADHD, BPD, bipolar, PTSD. However, due to its deep locations in the medial temporal lobe, it has been very challenging to targeting these regions for treatment. Invasive treatments such as deep brain stimulation provides very direct targeting for treatments in some treatment-resistant disorders, has shown some efficacy. However, the widespread use of these invasive treatments in the patients with treatment-resistant disorders is impractical, not mentioning the inherent risks associated with the neurosurgery. In contrast, the non-invasive treatments, such as the TMS, has less limitations on the widespread use and avoid the necessity of neurosurgery. However, the targeting of the deep regions precision is disappointing. So we still need definitive empirical evidence for the development of a strategy that can non-invasively and precisely targeting and modulate the subcortical regions. To address these critical needs, we leverage the multimodal approach by combining several invasive and non-invasive brain stimulation and recording methods. We started with the intracranial electrical stimulation concurrent with the intracranial IEG. With this method, we can deliver the direct stimulation to the cortical region and concurrently recording the activity in subcortical regions with the electrodes implanted in these two regions in epileptic patients. The direct stimulation also offers minimum perceptual effects that can often seen in other stimulation methods. To move towards the clinical translatability, we replaced the IES with TMS. That is the second method shown here, but still recording the subcortical activity with the intracranial IEG. However, as we know that the IEG can only be used in epilepsy patients, so it is necessary to combine the TMS with a non-invasive brain measurement to map the effects of TMS in a broad, healthy population. The concurrent TMS fMRI is a well-established method that allows us to deliver the TMS to a cortical region of participants in the scanner and to measure the subcortical region's activity with fMRI. So with these three methods together, we can provide definitive empirical evidence of the target engagement for the subcortical regions. Furthermore, we also evaluated the relationship between the individual functional connectivity assessed with the resting state fMRI and the target engagement assessed with these three methods I described just now. With all these three methods, we delivered the single pulse stimulations to induce transient neural changes as a proof for the target engagement. In the present talk, I will just focus on two pathways that we are currently working on. The first is the DLPOC to the amygdala. This pathway has been demonstrated in a small sample size with concurrent TMS-fMRI in my previous work. And the second is the parietal cortex to the hippocampus, which has been investigated by Joe Wall's group, just shown in Andrew's slides. So for the first pathway, my first-year graduate, Xianqing Liu, will present her poster on Wednesday and Thursday. So if you are interested in, please stop by for more details. And here I will just highlight some main findings. I will start with the concurrent IES-IEG. We delivered the IES to the DLPOC and concurrently recorded the amygdala connectivity. As shown in this two plots, we can see that about 50% electrodes in the amygdala showed evoked potentials amplitude exceeding 10 standard deviation with respect to the baseline. And this effect was mainly contributed by the medial subregion. As a control, we also delivered the IES to the VLPOC, which is very close to the DLPOC. We also see 50% electrodes of the amygdala showed 10 standard deviation with respect to the baseline. However, we didn't see evident difference between the responses between medial subregion and lateral subregion. In the second step, we directly compared the evoked potentials following DLPFC IES and VLPFC IES. As labeled with the dotted line and the solid line and dotted line in the charts. So we can see that there were two time windows showing significantly higher responses following the DLPFC IES as compared to the VLPFC IES. And this effect was mainly driven by the responses in the medial subregion. With the second method, concurrent TMS IEEG, we delivered both the TMS, active TMS and sham TMS to the DLPFC. We also tracked the evoked potentials with the electrodes in the amygdala. And we again observed over 60% electrodes in the amygdala showing evoked potential amplitude exceeding 5 standard deviation with respect to the baseline. And this effect was again mainly driven by the medial amygdala. And this pattern was not seen with the sham condition. As a second control, we delivered both the active TMS and sham TMS to the parietal cortex. We also didn't see similar pattern as seen with the DLPFC TMS. With a direct comparison between the DLPFC versus parietal TMS evoked potentials, we also see two time windows showing significant differences following the DLPFC TMS versus parietal TMS. Again, this effect was mainly driven by the medial amygdala. So with the third method, we are able to acquire more participants in the healthy population, and we also delivered the TMS to the anterior DLPFC and posterior DLPFC with high spatial resolution. We also delivered the TMS to the right inferior parietal lobe as a control. We concurrently measure the amygdala responses with fMRI when participants are in the scanner. The results showed that there was a significant main effect on the TMS size. So post-hoc analysis showed that both the anterior DLPFC and posterior PFC showed significantly higher TMS evoked fMRI responses in the amygdala as compared to that following the TMS to the right IPL. So in the final step, as mentioned, we also evaluated the relationship between the individual functional connectivity and the amygdala responses. So first, we extracted the DLPFC IES evoked potentials from the two significant time windows and compared them with the DLPFC amygdala functional connectivity. We found that only in the early time window, there was a significant correlation between the FC and amygdala responses. That is, the stronger negative functional connectivity between the DLPFC amygdala was associated with the great responses in the amygdala. However, this was not seen in the late time window. We also compared the intracranial intracranial DLPFC TMS evoked potentials with the DLPFC amygdala functional connectivity for the two significant time windows. Again, we see that there was a significant correlation between the FC and amygdala responses, but not seeing this correlation in the late time window. As just mentioned, that with larger sample size and high spatial resolution provided by the concurrent TMS-FMI, we were able to dissociate the different parts of the DLPFC effects, TMS effects. So we compared the responses in the amygdala evoked by the anterior DLPFC TMS and posterior DLPFC and right IPL with the connectivity between the stimulation site and the amygdala. Surprisingly, we see that only the posterior DLPFC TMS evoked FMI responses in the amygdala was significantly correlated with the functional connectivity. This was not seen in other two stimulation sites. So next, I will also highlight some main findings for our second neural pathways. We also used the concurrent TMS IEEG to deliver the TMS to the parietal area in two subjects groups. In the first subject group, we delivered the FC-guided parietal TMS. In the other subject group, we delivered the non-FC-guided parietal TMS. In the FC-guided parietal TMS, we defined the FC-guided parietal stimulation site as the parietal spot with the maximum connectivity with a hippocampal electrode. Our results identified that as compared to the shine condition, the FC-guided parietal TMS condition induced significantly higher or stronger responses in the hippocampus in 3 time windows. In contrast, the non-FC-guided parietal TMS did not evoke similar evoked potentials. We further compared the intracranial TMS evoked potential in the hippocampus with the parietal hippocampus functional connectivity. And we found that there was only in the middle time window there was a significant correlation between the functional connectivity and the responses in the hippocampus. That is, the stronger positive functional connectivity was associated with the great responses. This was not seen in the early time window and late time window. To further validate the importance of the hippocampal FC-guided TMS, we also conducted a second experiment with the concurrent the TMS-FMI. By delivering the TMS to a non-hippocampal FC-guided stimulation site, that is also within the parietal, but is the inferior parietal lobe. And we also delivered the TMS to the right M1 as a control. As expected, we didn't observe significant, on the group level, we didn't observe the significant responses in the hippocampus when delivering the TMS to the right IPO. This is the same as the TMS condition for the right M1. However, very interestingly, we found that there was a significant functional connectivity between there was a significant correlation between the functional connectivity and the hippocampal responses. So that is the strong positive functional activity between the right IPL stimulation site and the right hippocampus there was great activation in right hippocampus. This was not the case for the right IPL to left hippocampus part, neither for the pathways of right M1 TMSIs to either side of the hippocampus. To summarize, our two projects together provided definitive and convergent evidence of subcortical target engagement by selective and multimodal cortical stimulation. The relationship between the individual stim target FC and target engagement suggests a potential personalized FC guided strategy to pinpoint a cortical site accessible for non-invasive stimulation, thus modulating the subcortical regions we are interested in. So we also have some ongoing work, and we plan to present in the future. So please stay tuned. Finally, I would like to take this moment to thank my colleagues in Iowa community and my collaborators from Stanford, Harvard, and also especially thank my lovely lab members. The work I presented today were all done by them together, so I'm very proud of them. And finally, thanks for the sponsorship from NIH and BBRF. Thank you for your listening. I'd like to take questions later.
Okay, thank you very much, Jing. Okay, so the next speaker is myself. Take the privilege that demonstrated some of our recent work. And so basically what I'm going to talk about is big data guided, individualized TMI target precise intervention for depression. So in our lab, the main focus is major depressive disorder. And in China, according to the prevalence, is 0.5% of Chinese MDD patients were treated adequately. They get the condition, they will go to hospital, they will take medication, and they will continue the treatment. Very few of them. Even those people, they have adequate treatment, the first kind of medication, only 30% can get a good response. And another 1/3, they need to switch the medication and finally find a suitable medication. And there's still 30% of the patients, they will fail any kind of treatment according to the literature. The 1/3 of the depressed patients, they will labeled as treatment-resistant depressed patients, very difficult to treat. And there's one way to help treatment-resistant depressed patients is TMIs. And Angel already demonstrated you how we can use TMIs to better stimulate the brain. And here's the slides. Angel already showed you that mostly currently in practice is use a 5 centimeter way, have the motor area and a 5 centimeter height. It's pretty imprecise. And in the future, as Angel already talked from the B3 or from the anatomical, but in the future is each of us have a distinct brain. We should find our individualized target to have a better treatment, to increase the TMS treatment response. So how to find an individualized target is still a problem for the field. And Angel already showed these slides that proposed by Michael Fox that using subgenuine ACC, a deep structure, we do functional connectivity. And we find a functional connectivity that's related to clinical improvement of TMIs. But there's one problem there, is only very few studies have used individualized restorative MRI to get treatment. But maybe we should work together more to increase the individualized treatment studies. There's also one problem there. If we use subgenuine ACC is at a very messy area. the signal of noise ratio is pretty low at the subgenuine ACC. This is also probably why if we use subgenuine ACC as a seat to do the functional connectivity at the DPFC, it's not so reliable. And there's some method like SeedMap and Angel. I already showed you Robin Cash developed some algorithms to make better identify the target. Then one way or another is why driving this front line ahead is inspired by this study by Noran Williams' group, the Stanford Neuromodulation Therapy. This study showed us using the accelerated TMS with individual TMS target, it can have very good benefit for the treatment-resistant depressed patients. So this is the algorithm itself. I didn't find it the public code online, so we need to implement by our best guess. But we combine this individualizing target algorithm and with the accelerated method that 5 days, each day 10 stimulations, stimulated 10 minutes, rest 15 minutes, stimulated 10 minutes, rest 15 minutes, 10 hours per day, and in 5 days. It's pretty intensive. And it's reported that about 90% patients with treatment-resistant depression has a pretty good response in this kind of SNT protocol. And FDA already has a clearance given to SNT, so this gives us a very good hope in the future you can find a better way to treat treatment-resistant depressed patients. So what we found to find individualized TMS target, we want it precise, we want it stable, like Angel already demonstrated. And also, we know individual data is pretty noisy, and Angel showed you maybe 15 to 20 minutes will be better, but mostly in our current group, the scan is not that long. So on the other hand, we have pretty large big data for depressed patients' brain imaging. Can we use big data of depression imaging to guide or to weight the individualized data to make a more extensible TMS algorithm? So leverage our direct depression image research consortium, we have accumulated pretty large data in our phase 1. If you want to have access to open source depression imaging data, you can access this website. We have our phase 1 already open accessed. And each participant in the hospital is jointly share their raw data. We will train their students to use our standardized protocol to process the data and share the final results, and we have big data to analysis. And for the phase 2 is the same mechanism. We have even more data. We have 1,600 and 1,300 healthy controls. Leveraging with this big data, so we think about to answer a question. We always think about using subgenuine ACC to find a DPFC target. But is there a real group difference or abnormality in DRPFC, SGACC function connectivity? So leveraging with this large-scale dataset, we did find MDD-related DRPFC abnormality in SGACC function connectivity. You can see these two spots, and we found the two clusters. Although we've also found SGACC connectivity that has lots of abnormality with the hippocampus or temporal areas. And, as literature showed that stimulating DRPFC, we focus on our algorithm on the DRPFC. And those two clusters is pretty at previous literature, they will stimulate this kind of area. And because Mike Fox said that in the previous literature can use individual data with a large group of data, maybe 1,000 household controls, to find the best SGACC, DRPFC coordinate. So we also utilize this data in our data. And we found the coordinate find SGACC is different from the MDD group to the healthy control group. The healthy control group is pretty like the Mac Fox reported. So we think maybe in the future we need to use the MDD group instead. And another way is we can utilize the group difference map. We compare the MDD group with the healthy control group. We can find the difference or find the abnormality. We can use that to get a coordinate or get individualization. And we found that this kind of group difference has clinical relevance. And this abnormality is correlated with the clinical improvement in the TRD dataset. And in another, the depression with the suicidal ideation SAD TMS dataset. And guided with this, if this map has clinical relevance, can we use this big data guided? For example, we have pre-processing, we have big data, we have group differences. Once we have group differences, can we get individualized targeting? We're using dual regression methods, using a group abnormality to find individualized target. And once we found the individual target, as Andrew already showed you, that can use this individual target offset distance and to correlate it with the clinical response. So here on the x-axis, the bigger, that means that the actual stimulation set is far away from all individualized algorithm computed target. And at there, this is treatment outcome. So the more far away from the computed target, the worse the treatment effect if using the individual target method. Also, we can use a group target. Seems there's some relationship. The offset target distance is correlated with treatment response, but using the individualizing target seems better than using the group target. This is on the Xi'an dataset using the depression patients with a suicidal ideation. And also, Eduardo pioneered in open science and TMS neuroimaging, so we also use Eduardo's dataset. This is drug abuse data, but they also have the depression scale. So we want to find if this correlated with the offset target, the distance. Once again, we found the offset, the target distance is correlated with treatment response. The more close with all individual targets, the better the response. So we have proved this on 2 different data sets. However, although we implement the SNT method, seems our method is better, but we need to prove this into longitudinal prospective study. So in the direct consortium, we launched an individualized precise TMS clinical trial. And we have TMS robot, and we will support the algorithm. And we have the International Conference on Brain Imaging of Depression. We have a coordination system there. And in our Institute of Psychology, we started this clinical trial. We have a TMS robot, which once we calculated the coordinate, the robot will place a coil to accurately stimulate a target. And we recruited lots of treatment-resistant depressed patients. They are pretty frustrating because medication doesn't work for them. And this is the interview. And what we found, we just finished 10 patients. 10 patients with this treatment-resistant depression. And we simply using all algorithm with a robotic arm. And we found all the 10 subjects had pretty good response in the 5 days, the TMS stimulation. And this is before and after Hamilton depression or Hamilton anxiety. Seems pretty good for them. And also, so it seems that we have longitudinal follow-up. We will follow up with them weeks by weeks. And it seems most of them in the depression scale, they maintained pretty well. Although longer data, in the half years, we found some people is getting started to go to back depression, but most of them can maintain pretty good long effect. And this is anxiety. Most of them, the 10 patients have pretty good maintenance in depression and in anxiety, that kind of symptom relief. So we hope in the future this can change the practice. Exactly that in the future, as I'm brain imager here, I would like maybe we can scan the brain to see what kind of method is suitable for them, psychotherapy or using medication, which kind of medication, or need to go to TMS, and we find a TMS target for them to better treat them and create a supporting network. And this is some documentary on TV for our group, and I would like to thank funding agencies and my students. And lastly is a development for our institute. 我换成中文说，就是如果参加我们中国科学院心理所的第4届认知与发展心理学青年论坛，可以扫描这2维码报名，我们会包机票和食宿。然后当然你如果自己正好也在回国，也欢迎来参加啊。And another slide is from Sensibility. They asked me to show you Sensibility is a very good journal. If you have good work, you can submit to there. And Sensibility also launched a sister journal called Medicine Plus. You can also submit your good work to Medicine Plus. Okay, thank you very much for your attention. So now let's enter into the panel discussion. If you have questions, you can go to the microphone to ask. And maybe you start some more closed panel discussion, and the audience may ask questions. Actually, I have a question annoying me a lot, that how far away do you think our work can really help people go to clinical practice? How far away?
I mean, from my perspective, I think that it's already, at least we've in Australia, we've established a clinic already where we're implementing TMS, fMRI-based TMS personalization, and we've already had somewhere in the order of 90 patients that have passed through the clinic that have benefited from this approach. I mean, that said, there is still a huge amount of work that needs to be done to progress this, and we still don't have a large-scale clinical trial of personalization in neurostimulation. So that's something that's certainly needed. So I think we're close, and to some extent, I think we're already there, in that it is possible for patients to benefit from these approaches. But that said, you know, we don't know a lot about the underlying mechanisms of how this is working. I think there is a lot of scope to still utilize structural connectivity and tractography. I think we've focused a lot on the functional connectome and functional and resting state fMRI, and I think there's still a lot of potential for structural connectivity and potential other markers to help us out here as well. I don't know if no other speakers might want to comments on that.
Yeah, I also think we need more studies, because I mean, we're seeing responses when we simulate, and we think we're simulating the circuits. However, I mean, in my experience and also other people's experience, at 6 months, everything goes back, or at least similar to baseline. So I mean, we were hoping there were going to be some advantages of having individualized, this type of individualized simulation, and then it was going to get some type of changes in the circuit, long-term potentiation, blah, blah, blah. I'm not seeing it. So I think we still need to know more about this, and maybe that it's also different depending on the pathology, like depression versus addiction might be different too. So yeah, I think in a sense we can apply it now to the clinic. In another sense, I think, yeah, we need more work.
Yeah, I think the SGACC FC guided stimulation is not novel, right? It's very famous now, right? So my point of view is that when you use the SGACC guided stimulation site, to stimulate the DLPC, and then finally, what brain regions were affected, and then whether these regions are associated with the which regions are really associated with the treatment effect. So I agree with Andrew's at least one point. We need more mechanism studies to prove this. Yeah.
So in fact, for the clinical practice, TMS now is very popular. So, but the big question is how to improve the outcome. This is everyone, for example, doctor, try to push this kind of things, maybe more patient accepted. But now this is, especially in China, I don't think this is very acceptable. So I think this is a big problem. So in future, we need to use this FMR, diffusion MR, especially maybe some Brainnetome atlas or this kind of things to change this kind of situation.
Another question is, today we talk about a lot of disorders, depression, drug abuse, maybe somebody is doing autism or maybe ADHD in the future. But for another hand, because we are talking about brain imaging-guided deep brain, can you imagine in the future, can we do enhancement? For example, tomorrow I'm going to have an examination. Can I stimulate, I will be more focused or have better memory tomorrow? Or for some kind of jobs, stimulate the brain, have better or more clever. So you imagine in that kind of direction, using TMS or other brain stimulation method to enhance our ability or even read or write our memory like a sci-fi.
I mean, I guess it could be used that way. Again, if we don't know the mechanisms and we don't know the extent of it, but I think some people are I'm guessing some people is using it for like memory, for example, to increase memory or at least well-being in general. I think some people are using it for that. I mean, there is still the hypothesis that it's not actually the circuits that are actually doing the work, but it's actually the dopamine release in general. So that's also something that maybe people don't want to talk about that much or study, but I think it might be important because maybe it doesn't matter where you stimulate that much as, you know, as which system of neurotransmitter you're actually, you know, stimulating. I don't know, maybe.
Yeah, I tend to agree with Eduardo. I mean, one criticism of these approaches is that targeting itself may not be particularly important. It's mainly that perhaps the TMS is simply a reset or a dopamine release, and so whether we're 1 millimeter this way or 1 millimeter that way, perhaps it doesn't matter. I mean, in terms of enhancements, I think there has been studies. I mean, we were involved in a memory study where the idea was to stimulate not directly, but to stimulate the science paper. That was not us, but we then did a follow-up where we looked at the effect of optimizing the site and what effect that would have, and there was some evidence that optimization would benefit. I mean, looking at very futuristically, I think I came across an article before traveling here where the defense is interested in these stimulation approaches where a soldier would have TMS coils embedded in their helmet, and so this would make them psychologically stronger or less vulnerable to the effects of pain or others. So I mean, I think that the future is potentially very, there are many diverse applications that might emerge from this, not necessarily clinically, but in other fields as well. So.
Hi, thanks for organizing the event and thanks for the great talks. I'm Zhing Jiang from Beijing Anding Hospital. I want to hear your opinions about two questions. The first is, what do you think about the impact of the noisy personal data to the precise targeting? Because when we collect data, we cannot guarantee that the data is always as good as a group average. So what's the extent of the impact to personalized localization? This is question one. And question two is, what do you think about the dose effect? Which is more important, the dose effect or the precision of the targeting? Because Morris has published a paper this year on Nature Medicine comparing fMRI-guided targeting and traditional TMS, traditional ITBS, and found they have equivalent effect on TRD. Thank you.
I mean, I think they're both excellent questions, and in a nutshell, if the data quality, if our fMRI data is poor quality, we're not going to be able to localize with any kind of reliability or precision. So we've done some simulation studies that are focused on the length of the fMRI acquisition, and so if we have our short 5 or 6 minutes, that's typically not enough to enable accurate personalization. There are other factors as well that can contribute. It's not only the length, but also the type of acquisition, the TR time, and so on. These can also impact on the quality and the reliability of a target. So that's absolutely, it's a critical point. We need to ensure that we have high quality data, and I also agree that may be difficult to do in a clinical context, right? A patient might be more vulnerable or more susceptible to moving within the scanner, or there might be other constraints that would prevent us from acquiring 15 minutes of data in a patient, and so maybe we only have 5 minutes of data. That's the best that we can do. Moving on to the second question, I think you raised whether a dose effect would perhaps be more important than personalization. I don't know. I mean, I think these are complementary. I think that an adequate dose, as well as precise targeting, would be the best possible outcome. They're not mutually exclusive, and I think dose is an important issue, and this has come up with the new intents, the SAINT protocol, and so on. We've also found this in a recent study in OCD, where we started the trial with what we believe now was a dose that was too low, and so in retrospect we should have used a substantially higher TMS dose to begin with. So I think these are both critical issues, and they're not mutually exclusive. It's not that we can't have personalization without a particular dose. I think we can have an adequate dose and also ensure that we do have a good target, a stimulation target. Perhaps.
So for your first question, so in fact, if we based on the functional MRI, so this is a big problem. So I don't think this can be addressed. This is intrinsic. But if we use differential MRI, so I suggest the Brainnetome Atlas guided. So this is very easy to address. So no any, because differential MRI is very stable.
Yeah, I wanted to say that. Oh, sorry, Chao-Gan, going. Okay. No, I wanted to say that I think dosage is more important. I think it is because even though we don't have precise medicine at the moment with TMS, we still get people getting better. So it might be that they're both important, but I think dosage might be more important because of that. But also I think one important issue is the cost for the patients in the future, because we found that functional connectivity is the best to do this, you have to get an MRI for each patient, and depending on the country, you will have a different price and cost for the patient. Some governments will be able to absorb it, some others won't. So I think that's an important issue, because then it doesn't matter if you have precise medicine if you can't afford it, I think.
I also have a comment for the first question is, One way is we are trying to use big data because if bigger data is more reliable a little bit, right? So we use that to weight the individual data. The individual data is noisy, but you use big data results to weight the individual data. That might increase a little bit the reliability. And in the future, we can use machine learning methods to learn the backbone of maybe tens of thousands of people, the brain, the backbone, what it should be, and impose that on individual data might be increase the reliability. This is my thought, and my lab is trying to do. Okay. Okay, because our time is running up. Our time is up, so please join me thank the presenters and thank all the audience for coming to our Chinese Young Scholars event. And we hope next year we can have it again with another topic. And if you signed up for the dinner, please join us. Go to the Bravo dinner. Thank you very much.